So now that we have our definition of the limit, we can talk about continuity. When is a function continuous? And there's a simple analogy for this, that if you can imagine drawing a line, if you can draw that line without picking up your pen, then we would say it's continuous. But as soon as you pick up your pen, that point where you pick up your pen, we would then say it's discontinuous. So if I pull up a graph over here, and if we just follow the line on the left as if I'm drawing this out with a pen, I could draw this line without picking up my pen. But as soon as I get to x sub 3, I would have to pick up my pen, and so we would say it's discontinuous here. And then if I draw my line again, we are approaching an infinity here, and to get to the next part, I would have to pick up my pen to start drawing this next line. And so we would say it's discontinuous at x sub 4. So x sub 3 is a gap. The book calls this a jump discontinuity. And x sub 4 is a vertical asymptote where it's going to infinity. And these are places where the function is discontinuous. And if we draw the rest of the line, so we can draw this down, and then we get to this hole, and we would have to pick up our pen to go around this hole to start drawing again. So a hole is a point where we would have to pick up our pen, and a hole is discontinuous. So at x sub 6, we would have a discontinuity. So this graph you're seeing here has 3 discontinuities. X sub 3, we got a gap. X sub 4, we got a vertical asymptote. And x sub 6, we got a hole. And there is, of course, a precise definition for continuity in math. And that is these 3 statements. And let's just go through them. The first statement says, remember, C is our point of interest. F of x is the function. So this is saying the function must exist at our point of interest. That's all one is saying. The function must exist at the point of interest. And number 2 is saying the same thing, but for limits. It's saying the limit must exist at our point of interest. So the function must exist and the limit must exist at our point of interest. And then finally 3 says, at the point of interest, the function and the limit must equal. And if those 3 things are satisfied, then we would say the function is continuous. If one of those things is not satisfied, just one of them, then we would say it's discontinuous. So just looking at our graph to the right here again, if we look at x sub 3, why is this discontinuous? Well, our first statement, the function does exist. It exists right here. There's the function output at a closed circle. So it satisfies 1. If we look at 2, this is a 2-sided limit. Both of these are. And if we look at the 2-sided limit, that's what fails here. So the left limit is down here, and then the right limit is up here. They don't equal, and so the 2-sided limit doesn't exist. And so it's actually property 2 here that fails for a gap. And what about x sub 4? Why is this discontinuous? Well, the function doesn't exist at vertical asymptotes because that's division by 0. So the function doesn't exist. And also the limit doesn't exist. This is a limit we would say is going to infinity. And then finally, if we look at the last discontinuity at x sub 6, the limit does exist at holes. However, property 1, the function does not exist at a hole. That's what causes the hole, that the function doesn't exist there. So a hole fails then property 1. And these are the 3 things we want to look for if we want to determine that something is continuous. So I do want to go over again what are things you should look for in graphs that will be signs that something is a limit or continuous, or not a limit or discontinuous. So let's look at graph A over here. I showed this one previously, but I just want to go over this again. That I would just call this a regular old function. That's what you're seeing. For B, there is a hole here, and in general, I just call this a hole function. It's got a hole in it. And same with C. I would just call this, in general, a hole function. It's got another hole in it. And there is a point up here. The point only affects the function output. The point never affects the limit, though. The limit is always here on the line, in this case. And for D, that I would call a gap. So where the function is here, it's up here, and there's a gap that causes them to no longer be connected. Look at E. That's a vertical asymptote. And F is the more unusual one, where you have all the oscillations that continue forever and ever in an ever smaller and smaller area. Pretty unusual. Don't see that one too much, though. And these are the things to look for. Do you have a hole? Do you have a gap? Do you have a vertical asymptote? Or is the function going off to infinity? And let's take a look at these things again and talk about when the two-sided limit does not exist. So two-sided limits do not exist at gaps, because the gap has a left and right-sided limit that don't equal. So gap, you see a gap? There's no two-sided limit there. Vertical asymptotes, there's no two-sided limit at a vertical asymptote, because the left and the right would be going off to infinity. And then oscillations. There's no two-sided limit at 0 here for these oscillations. For one-sided limits do not exist at vertical asymptotes and oscillations. One-sided limits do exist at gaps, because you can have the left-sided limit, which is one-sided, and the right side, which is one-sided. So you can have one-sided limits at gaps. And then finally, continuity. Continuity does not exist at holes. So a hole fails the first property, that the function does not exist. That's what creates the hole, that the function doesn't exist. So a function is discontinuous at a hole. At gaps, a function is discontinuous at gaps because the two-sided limit doesn't exist, which is property 2 of continuity. There's no continuity does not exist at vertical asymptotes. And this is because the function does not exist at a vertical asymptote. And continuity does also fail for the infinite oscillations, as the function does not exist in this case at 0, and nor does the two-sided limit. So let's check out some problems from the book. And these are just 1 through 4, good graph problems that I like to choose. And it simply states here, state whether the function graph is continuous on this interval. If not, where does it fail to be continuous and why? So they're asking for which property. So all these are from -1 to 3. And if we look at the first one, we have a solid line, so we're all good there. Here's our hole. So number 1, is the function graph continuous on the entire interval? No. If not, where does it fail? It fails at 2. Because there's our hole. And why? Well, this was property 1. The function does not exist. Let's look at number 2. Here's our line. Nice and solid, looking good. And then we get to our hole. So number 2. Is the function graph continuous on the entire interval? No. If not, where does it fail? Fails at 3. Because there's our hole. And why does it fail? It fails because the function does not exist at holes. Let's take a look at 3. 3 is a solid line. Looks good, looks good, looks good, looks good. All the way to the end, bang. One solid line. Is this function continuous on the entire interval? Yes. Didn't have to pick up my pencil once to draw that line. And then how about 4? So I'm drawing my line out. We got a hole. We got a gap. And then I'd have to draw my line again. So is this continuous on the entire interval? No. Where does it fail? It fails at 1. And why does this fail? Now here, for a gap, the function exists right here. The closed circle is where the function exists. So property 1 is satisfied of continuity, but the two-sided limit fails. So our limit from the left would be up here at about 1.5, and our limit from the right would be at 0. Those limits don't equal, and so the two-sided limit fails. So the limit here does not exist. And so just some graph problems there. Again, the telltale signs of what to look for: holes, gaps. No vertical asymptotes in this particular section here, though. So let's check out some different type of problems. The graph here, but some different questions. So number 5, part A. And here's our function. Does f of -1 exist? Well, here's -1. It's got a closed circle on it. So A, yes, the function does exist at -1. B, does the limit exist as we go to -1? So here's -1 from the right. There's our plus sign there. -1 from the right. Well, approaching from the right, we'd get closer and closer here. And as we get closer to -1, we'd be at an output of 0. And that would be the limit. So yes, does the limit exist at -1 from the right? Yes. C, how about -1 from the right? Does this equal f of -1? So does this limit equal the function output? Well, the function output at -1 is 0, and this right-sided limit is also 0. So yes, the limit and the function output equal. And then finally, is this function continuous at -1? And now Notice A, B, and C are all three of the properties. A, does the function exist? B, does the limit exist? C, does the function and limit equal at our point of interest? Yes. Is this continuous then? Yes. So how about number 6 then? Does f of 1 exist? So let's check out where 1 is. And if we look at the function output is where this point is, so a little goofy, got a gap there. But the function output is here, and the function output does exist. So how about B? Does the two-sided limit as we approach 1 exist? So here's 1. Approaching from the left, we find ourselves at a height of 2. Approaching from the right, we also find ourselves at a height of 2. The limit does exist at holes. So the two-sided limit does exist here, and it's 2. So yes, the two-sided limit does exist. Does this limit equal f of 1? Does the limit equal the function? Well, the two-sided limit is right here at the hole. The two-sided limit is 2, and the function output is 1. They do not equal. No, they do not equal. Is it continuous then? No. Since the function and the limit don't equal, then we would say this is discontinuous. So let's check out one where we don't have a graph and we just have a function. And so these problems are asking at what points are the function continuous? So they want to know the interval on which this is continuous. So we want to find, well, it's usually easier to find where it's discontinuous and then omit those from the domain. So let's take a look. And this goes back to then what causes things to be discontinuous. A hole does. Now a hole occurs when you have things divide out, and I'll show you that in a second here. Another thing is gaps, and gaps are pretty rare in a single function. They're more common in piecewise functions, and I'll give an example of that. And the other thing that could be is vertical asymptotes. Now there are other infinite oscillations. That's only going to happen with a trig function now. So no infinite oscillations here. So we're looking for, so there's no oscillations, there's no gap, because it's a single function here. And so all that's left is a hole or a vertical asymptote. And those things are caused if you have division by 0. So we want to look if we have division by 0 here. And how are we going to do that? Well, we're going to factor. So if we look at the bottom here and factor that, where do we have division by 0? So if we look at this, we can see then that there's division by 0 at 1 and 3. So 1 and 3 will cause division by 0. And division by 0 in this case is a vertical asymptote, and a function is discontinuous at vertical asymptotes. So at 1 and 3, this is where the function is discontinuous. Now they do want to know where it is continuous, and MyMathLab is most likely going to want that in interval notation. So this is continuous from minus infinity all the way up to 1, because it's discontinuous there. And then we're going to have to use the union symbol here. And then we're going to go from 1 to 3. We'll use a union symbol again because it's discontinuous at 3. And then we go from 3 to infinity. And so this is where it's continuous. So we omitted 1 and we omitted 3 because that causes division by 0, which is a vertical asymptote, which makes the function discontinuous. Now I do want to say something really quick about wholes, because wholes are also when you have a division by 0. And I'm going to change this plus to a minus though. So I'm just going to make up a different one. Now in this case, the x minus 1s will divide out. And this is then a whole function right here. So when you have x minus any number, so x minus c, if you have x minus c divided by an x minus c, and these divide out, that's a whole. If these don't divide out, like in the problem we just did, because that was a plus 1, then you have a vertical asymptote. So for this function here, I was just showing you how it simplifies. This function is still has the same domain for continuity. It's still continuous on this interval. But what's different now between our previous one is that this function has 2 vertical asymptotes. Has a vertical asymptote at 1, has a vertical asymptote at 3. But because these x minus 1s divide out, this is a whole. So this function has a whole at 1 and then a vertical asymptote at 3. And these whole functions are challenging to graph because I don't think any calculators actually graph a whole correctly. I know if I use my TI calculator, it just graphs it as a straight line, like as if there's no hole there. So those are difficult to see graph-wise with your calculator. And it might be actually easier to see if you have a hole by looking at the equation. So if you don't have a good tool to graph, Desmos, DES, is a great graphing program that I use a lot. And if we look over to the right here, using Desmos, here's what the plus 1 part of the function looks like. So there's our 2 vertical asymptotes, one at 1, one at 3. And now if we change this plus to a minus, now here's what the function looks like. So these x minus 1s, if you simplify, would cancel, but even Desmos doesn't draw the hole in here. So at x equals 1 is our hole. So right here where my mouse cursor is, there should be a hole. So pretty difficult to see those graphing-wise. So let's check out another one. At what points are this function continuous? So we're first going to look where it's discontinuous. And let's take a look at what that function is. So what are we looking for here? We're looking for division by 0. And is there division by 0? And there is a denominator here. So a potential for division by 0 because we have a denominator. But there is an absolute value sign on that x, which means it can never be negative. It will never have a negative output here. And so there's nothing that will subtract away 1. There's no way to make this denominator be 0. So there's no discontinuity there. And x squared is a polynomial. There's no division by 0 there. So there's no division by 0 anywhere here, which means there's no hole, there's no vertical asymptote. So if we pull up the graph of this function, we can see we can draw this function without picking up our pen, and it is everywhere continuous. And so that would be our answer. Nowhere is it discontinuous. There's no hole. There's no vertical asymptote. Those things are caused by division by 0, and there's no division by 0. There's no gap, which for single functions normally happens at also a division by 0 somewhere. So there's no gap. And there's no infinite oscillations, which would require a trig function. There's no trig function here. So just things to look for in your function. So let's check out a trig function. At what points is this continuous? And now the easier thing to do here is to determine where it's discontinuous and then omit those points. And we're going to be looking for division by 0. That's pretty much our telltale sign of something to investigate. So here's our function. And when do we have division by 0? So the cosine function, when is the cosine function 0? So if I pull up a graph here of cosine here, it starts at the top, goes and ends at the top again, so that's one period. And it's 0 at pi over 2, and 0 again at 3 pi over 2. So cosine is 0 at pi over 2, and then 3 pi over 2. And what about after that? So we have pi over 2, 3 pi over 2, and then we have 5 pi over 2. And then by looking at the pattern here, 1, 3, 5, you can see the next one's going to be 7. And then 9, and 11, and so on and so on. There are infinitely many zeros here. And this is where they're located on the right. All the zeros on the left would be at the negative values here. So we would say that this is discontinuous to indicate all of these values. We would then throw an n in here. And we would say this is discontinuous for n times pi over 2, where n is an odd integer. So again, cosine is 0 in infinitely many places. And then we have to list all of those out. I listed here the places on the positive side. And the negative side just means the negative of all these numbers. You can see 1, 3, 5, 7, these are all odd integers. And so an odd integer n times pi over 2 gives us all the locations of the zeros. And so looking at what they want for the answer here, they want the answer to be that it's continuous everywhere except where it's discontinuous, this statement then. So let me show this function, x plus 2 divided by cosine x. Here's what it looks like. It's pretty interesting. You can see it's got infinitely many vertical asymptotes. All these vertical asymptotes are located at n pi over 2, where n is an odd integer. So this function is continuous everywhere except where we have these vertical asymptotes. And that's our answer. Let's check out another one. And this one is a piecewise function. And in piecewise functions is where there's a strong potential for a gap then. So there's no guarantee as we go from, say, this top piece to the middle piece, there's no guarantee that these pieces touch. And so there could be a gap there. And how would we determine that? Well, we could graph it, which I'll show you in a moment. But algebraically, we want to look at where this first piece ends. Where does the transition occur? And the transition occurs at 0. So right as we hit 0, we leave the top piece and we go to the middle piece. So 0 is a point of interest where there could be a gap. And so we need to check, what does the top function equal when we have a gap? Well, right at that point, x is 0. So we would have 1 minus, and right at the point of change is 0. And so this top piece equals 1 right at the point of change. And then we'll look at the second piece. And we're going to look at where the second piece begins. So the second piece begins at 0. And so we plug that into the next piece, and e to the 0 is 1. And so what we see here is that this first piece ends at 1, and the next piece starts at 1. So these pieces touch, and there's no gap. So there's no gap at 0. At 0, these pieces touch. So now we need to check the next transition, where we go from the middle piece to the bottom piece. And that transition occurs at 1. So at 1, we leave the middle piece and we go to the bottom piece. So we need to check that out. What is this middle piece right as we transition to the next? And that's at 1, and e to the 1 is e. So the second piece ends at a value of e. And where does the third piece begin? Well, the third piece begins at 1 squared plus 2, which equals 3. And 3 does not equal e. So when we go from the middle piece to the third piece, these don't touch because the middle piece ends at E and then the next piece starts at 3. So there must be a gap here because these pieces don't touch. So let me show you what that graph looks like. Here it is from Desmos. Here's our linear function cruising along until we get to 0. At 0, we change to the exponential. And then at 1, we change to the quadratic. And then you can see there is our gap. The exponential does not touch the quadratic. And then there's a gap. And so we then say this is discontinuous at 1. Now, the problem does say where it's continuous. So let's now answer that. We know it's continuous everywhere but 1. And so we're writing that in interval notation. It's continuous everywhere but 1. And that's our answer. At what points are the function continuous? It's continuous everywhere except 1, the point we omitted. So let's check out one more. And I have to say, I really like this type of problem. I guarantee it. You'll see it on the test. So for what value of b, so here's our piecewise function, for what value of b is this everywhere continuous? Now I'm going to make up some value for b so I can just graph it and show you. So here we go. I just made up some value for b. So here's our quadratic. Here's the linear function. You can see there's a huge gap here. What we want to do is we want to choose b in such a way that these two functions will touch. And so that's what we're going to do. And how can we do that? What does it mean mathematically for these equations to touch? What that means is at this point, -2, they must equal each other. So we have our equations. Now, we're not saying these equations equal everywhere, because they certainly don't. We want to know at what value of b will these touch when x is -2. So we want to know what value of b will make these touch at -2. And there's our equation. And so -2 squared is 4. And dividing both sides by 4, and then we can simplify that into a half. So let me show you what that graph looks like. So now I'm going to graph this with b is -1/2, and that's what it looks like. So to make these touch at -2, we actually had to flip the quadratic around, and you can see now they touch. And so now this piecewise function is everywhere continuous. We can draw this one line without picking up our pen. Let me just go through that really quick again. What did we do? We equated the two equations. So we set the two equations equal. But this is only true when x equals minus 2, because that's when we want them to touch. We only want them to touch at minus 2. So this equation, they only equal at minus 2. And then that's what I did. I plugged in minus 2 then into that equation and solved. And that gets us our b value to adjust these functions so they touch. And now it's everywhere continuous. So I think that's pretty cool. I like those. Expect to see this, maybe not this exact one, but definitely one of these on the test. And that is continuity. I do want to say one last thing in closing, that there are some minor topics in 2.5 in your book. You should be reading along in the book that I'm not talking about. They're not going to be useful for us going forward, and there's no homework problems on it either. But if you are interested more in math for your future, it is good to read a text and see the other things they're saying. And that finishes continuity.